Hello everybody. I think one of the most widely followed stories, at least this week, of a scientific nature has been the decision by Japanese authorities to release radioactive contaminated water into the ocean from the Fukushima nuclear reactor. Understandably, people are concerned and following the story closely. I thought, at least from my part, I would share with you some of the knowledge I have about the science of radiation, which hopefully will allow people to follow this story more closely. So, what is radiation? Well, to a physicist or a scientist, radiation ultimately is just energy. It can be energy in the form of a wave or in the form of a particle. That's a little different by what we mean from radioactive material like Fukushima. That's a more special type of radiation. In general, you can look at radiation as being either ionizing or non-ionizing. What does that mean? Well, ionizing radiation is essentially radiation with sufficient energy that is able to strip electrons from atoms. Why is that an important distinction? Well, that's effectively how radiation does damage to human beings, by tampering or interfering with the structure of DNA. That's ultimately what causes cancer from radiation. So it is ionizing radiation that we're really talking about when we're worried about radioactive material. But what actually is radiation? What actually is happening here? Well, radiation fundamentally occurs from isotopes or elements that are unstable. So certain types of element or certain atomic configurations are unstable. They're of higher energy, and they will need to release energy in order to reach a stable state. In order to get from a high energy unstable state to a lower energy stable state, they release energy outwards. And that energy release, that is radiation. But radiation comes in a number of forms. There's not just one type. Scientists classify radiation, in fact, in three categories: alpha, beta, and gamma. Alpha radiation is the emission of a helium nucleus. Beta radiation is the emission of, say, an electron. And gamma radiation is the emission of a photon, or a weightless particle, or something like an X-ray. All three of these types of radiation carry energy, but their properties are somewhat different, and that's why they're divided in this way. So first, alpha radiation, that's the helium nucleus. This is by far and away, the heaviest type of radiation. That's a big particle relative to, say, an electron, a helium nucleus. For this reason, it's quite energetic and can cause a lot of damage if it gets inside your body. However, also because it's a very big particle, it's very easily absorbed. So alpha radiation, in fact, if this object here was emitting alpha radiation and I held a piece of paper in front of it, in most circumstances that would be enough to absorb all of that alpha radiation. In other words, alpha radiation, whilst very damaging, is also quite easy to protect against. For that reason, alpha radiation causes the most problems when it's ingested in the human body. If it's ingested into the human body, then because the particle is very large, it actually it's a concentrated hit of energy into a relatively small area, and therefore can cause immense damage to cells and DNA in the area that's targeted by the alpha. However, if you're wearing any form of protective clothing, or indeed ordinary clothing, the alpha radiation is unlikely to penetrate and cause any damage. The second type of radiation is beta radiation. Beta radiation is the emission of an electron. Now, beta radiation is probably quite relevant in the Fukushima example because it's, at least if the reports are to be believed, seems to be the predominant radioactive emission mechanism involved. In Fukushima, it's mainly, we believe, tritium that's being pumped into the ocean, and tritium is a beta emitter, so it emits electrons. Now, beta radiation, being an electron, is significantly smaller than alpha, which is a helium nucleus. So an electron will have more penetrating power than alpha radiation. However, in most circumstances, ordinary clothing or your skin is enough to block it or absorb it before it reaches the inside of your body. So beta radiation, like alpha, causes the most harm to human beings when it's ingested. And much of the concern around Fukushima is because it's in water, right? And water is an ingested object. The final type of radiation is gamma radiation. Gamma radiation is a photon, or something like an X-ray. So this is a massless particle. You can think of just pure energy. This is the most tricky because it takes a lot to absorb this. In fact, you can have several inches of concrete or lead and a bit of a distance between you and the radioactive object, and still gamma radiation can get through. And if you're not protected at all, or just wearing ordinary clothing or even protective clothing, the gamma radiation will be passing straight through your body. So in most circumstances, many scientists regard this as one of the more dangerous types of radiation, simply because it's just very hard to protect against. You don't have to ingest it for it to cause a lot of damage to you. That's the basic facts of radiation, and you want to know the half-life, because that tells you about effectively how long is it going to be in the environment. That half-life statistic is very important when you consider the potential damage radioactive substance can cause. Whilst very short half-life substances can emit very intense radiation, it's only emitted for a very short amount of time. What tends to cause people a lot of trouble, and where radiation can build, for example, in the food chains or last for a very long time in the environment, is long half-life radioactive substances. These are substances that decay over periods of perhaps tens of years, and therefore they just build up in animals and plants that absorb them. And it's actually it takes a long time for areas that are contaminated by long half-life radiation to become habitable or safe again, if the radiation is in significant quantities. So they're the main properties of radiation. Is it alpha, beta, gamma? What's its half-life? And you also look at the energy of the particle emitted. And those three together effectively will determine how much of an environmental concern it is and how much damage it could cause if it gets inside the human body and starts interfering with your DNA, which is the source of cancer. So hopefully, as you read these articles in the coming weeks and people talk about radioactive tritium with a half-life of 12 years and so on and so forth, that this will help you understand exactly what those words are meaning.